Okay, guys, so we're on live now. I want to welcome everybody to the class. You should be, this is AC circuit analysis, and I think I have about eight people enrolled. I think we're missing a few people, so we'll see what happens with that. You should have had a course in circuit analysis. I went over the list. I think most of you, I think you've had me last semester at some point. You had me for Circuits 1. So there is a prerequisite for that. You want to make sure you've had Circuits 1. And you should have had a course in algebra and trigonometry with a focus on the trig. That's a big part of the course. So what I want to do is, before we get into the lecture, I want to go over a few things that you're going to need. There's been some changes made. I know if you had a class over the spring semester, especially if you had my class or a technical class in the ET department, then we did some stuff with simulation software, and there was a bunch of ways we did uploaded assignments. And so I kind of want to go over some of that, and I think the dust is kind of settled now, and we have a approach that we're going to apply. So I want to go over some things with you. Before I start that, you want to make sure you go over the syllabus. Normally on the first day of class, if we were at the school, I would project the syllabus on the board and we could go over it. So I think, like I said, I think I had most of you before, but there's one or two people whose name I don't recognize. You may have been in my course before. You definitely want to go look at the syllabus. Just to point out a couple things in the syllabus. Number one, there's listed on the syllabus 4 exams. Normally in all my courses, I'll have 4 exams. I'm not sure that I'm going to work it out that way. I don't honestly right now. I don't know. Ideally 4 exams is nice. That means each exam isn't weighted so heavily. So if you mess something up, it doesn't have such a drastic effect on your grade. But since the semester has been reduced to 10 weeks, I'm not sure that we can actually fit 4 exams in there unless I do something, special. We'll see. So I'll leave it at 4, but more than likely it might actually be 3, which I'm not happy about. But with the shorter time, we'll just have to see how that works out. So that's one thing. Make sure you go back and you look at the syllabus, the grading method. I grade on a 10-point scale. I do not curve anything. I don't drop anything. Well, I do drop something. I do drop 2 quizzes. So if you mess up on the quiz, I drop the 2 lowest quizzes. And also along the way, I give assignments that you can do, and they count as quizzes, but they're actually little extra credit assignments, but they count as a quiz grade. The idea there is if you mess a quiz up or a couple quizzes up, 2 of the lowest scores will be dropped, and then the other extra work I give you can take the place of a lower score quiz and kind of cancel that score out. So anything I give you like that, you want to make sure you do it. A couple things I've learned from doing things online. Number one, it's important that when you submit work, you submit it the way I asked for it, which is going to be through Blackboard. I won't take anything else from email because that was a nightmare. Last semester was a nightmare grading. I had people uploading stuff to Blackboard. People would miss the time deadline and they would email me, and it's a nightmare going through 1,000 emails trying to. I'm not going to do that this time. So I'm not going to take any late work. You'll know when things are due. When it's due, you'll have a link. You can upload the assignment to me, and then when I get the assignment, I'll grade it at some point. And if you miss the due date, you just have to take the 0. I won't take it by email. I won't even look at it in email. Now, if for some reason we have some kind of special agreement and we agree for you to email it to me, then I'll do that. But I had people miss the link. The link will disappear, and then they email it and they figure it's turned in. If it doesn't go in the Blackboard, upload it the way it's supposed to be. Then if it's emailed, I still consider it not turned in. So that's one change that I'm going to make. But I'll get into that. Let me go over the introduction here, and then we'll talk a little bit about some things that you'll need, and then we'll get into the actual course today. So I think I'm not going to make an introduction. I thought about making an introduction video for the syllabus. I'm not going to do that. But there is one important document on Blackboard. It's a packet that goes through and looks at the power distribution system. So since we're using this collaboration software, it doesn't really work well. It has the ability to share files, but I find that all this thing really can do is record us. So I'm not going to mess with it and try to share a file with you because I think I'll probably get knocked offline or it won't work right. So what I'm going to do is that document is kind of important. So I have the ability now. I purchased some software that allows me to capture my screen. I'll make a video of that packet, and there's some things on that packet I want to go over, and it'll be a nice review for what we do today. So I'll do that at some point, probably before next class, but definitely before the end of the week. You'll have that. So what will you learn in this class? Well, you'll learn a couple things. Number one, most of the stuff we did in DC, if you think about DC, we talked about Ohm's law in DC. We went through and we talked about series circuits. We talked about parallel circuits. Then we combined them and talked about series parallel circuits. And then once we did that, we figured out how to solve circuits with multiple voltage sources, and we Thevenized circuits. There was a lot of material. But pretty much we go through exactly the same thing, only we're using AC sources. And that the fact that we're using the AC source, and we'll talk about what AC means, just by the nature of changing from DC to AC, makes the things that we do a little more challenging. So you definitely got to be up on your P's and Q's to absorb the material and to get through it. This, of all the courses in electrical engineering or electrical technology, this is my favorite one to teach. If you go through it and you understand the concepts, some of the concepts are abstract and it takes a little while to get your mind wrapped around it. But if you really work hard and you understand the concepts, you'll come away from this course really, really satisfied, because this course, combined with DC, explains a whole lot of what goes on in the electrical world. And so I think you'll find it enjoyable, again, if you work hard. So there's a list of topics in the syllabus that talk about, actually list the topics and things that we'll go through. I'll leave that up to you to read it. But I think it pulls AC and DC together. It pulls concepts from DC, and it really sets a firm foundation for the rest of the courses that you'll take. In some colleges, you have to take DC and AC before you can take any other electrical course. So these really are foundation courses. So I think you'll enjoy it. The other thing here I have listed is attendance. Now, if you had me last semester, we started off meeting face-to-face. I don't know how many weeks we were face-to-face. But then that virus hit, and it was so much chaos because I didn't know how I was going to deliver the class. I had never talked to a camera before. It was new to everybody. So now things are in a little bit more order. But when we met in the beginning last semester, I was able to take attendance, pass the attendance sheet around. It turns out, I don't know if you guys realize it or not, but attendance is actually pretty important at Cincinnati State and actually all Ohio colleges. Because now the college receives money not by how many people it used to be by how many people enrolled, but they changed that formula maybe 5 years ago. Now it's how many people graduate. So they put a big emphasis on attendance. So I have to take attendance throughout the semester, but the main important times that the attendance is really looked at is the first 2 weeks. So I got to know that you were here for the first 2 weeks, because 2 weeks from today, they're going to ask me to turn my attendance records in. And if you're not marked as being here, if you receive financial aid, you won't get any financial aid, even if you were here. So I got to have a way of doing that. So what I'm going to do is have you guys, before we start lecturing, I'll have you guys send me a text with some information on it. And that's the way we'll do our attendance. So you send me the text, I'll go in every day, I'll write down the name of the text, and I'll know who was present for the lecture. So here's some things you'll need. And some of it, if you had me for DC or another course, you probably already have some of this stuff, but some of the stuff is going to be new. You're going to need a 3-ring binder, and normally all you need is a 3-ring binder, because when we're on campus, I'll print stuff out for you, and I'll punch the 3-hole punch it for you so you can put it in your 3-ring binder. Well, now I don't have the ability to do that because, well, I'm here and you're there. So I I don't have a way to print for you. So you need a 3-ring binder, and you need a 3-hole punch so that you can take documents, punch them, and put it in your 3-ring binder. Now, I have no idea if you actually have a 3-ring binder or not. So even though I'm saying it's required, it's really a strong suggestion, because I have people, even when we're face to face, I say, hey, you need a 3-ring binder. Probably 95% of the students get the 3-ring binder, but I have always 1 or 2 that they put papers in their folders. Well, I'll tell you this: if you think you have a lot of handouts last semester, just wait. Just wait. There's a lot of stuff, and you can easily get confused. But I think that 3-ring binder, if you take it, print it out, and put it in there in the order that we talk about it, in the order that I posted to Blackboard, trust me, it'll make your life a lot easier when you're trying to review or study for an exam or quiz. So you should get a 3-ring binder and the 3-hole punch. Now, having said that, there's no good to have a 3-ring binder and a 3-hole punch if you can't print the documents. So you got to have the ability to print. You either got to have a printer or you have to have access to a printer. Now, it's not something you need every day, but you do have to do that. This is unlike, of course, like English or something like that, where I can send you a document and you can type the answer. You know the nature of the beast if you had Circuits 1. Here, you got to be able to draw diagrams and to solve and do math on diagrams. So there's no way that I know how to tell you to do that on a computer screen. So you need the ability to print. So you either have to have a printer or you have to have access to a printer. Some of the quizzes I can probably set up, I don't know, as multiple choice, but most of the engineering type stuff, you actually have to draw circuits and work a problem. So you got to have the ability to print out an exam, write on the exam, and then resubmit it to me. So if that's an issue, then I don't know. It needs to be worked out some kind of way, and I don't know any way around it. So either you have to have a printer, or at least know someone that will give you access to it when you need it. You'll need now. This is, I'm not really happy about this, but so but I understand. There was a meeting between the professors in the EET department, and the meeting was for summer lab. Do we keep doing what we did last time, which was multi-sim, or do we do hands-on lab? Do we do hands-on lab and meet at the college for lab and do the lecture by video? And it was just a mess. So here's how it got worked out. And I'm not saying that this was the way I wanted to do it, but the majority rules. It was decided that you guys would need a analog to digital trainer and that you would do your labs at home. What happens is you'll need an analog, the trainer, which some of you already got for DC. I know for a fact some of you got it for DC. We didn't use it a lot, but some of you bought that for DC. So if you got it for DC, you'll definitely use it. But the problem is some of you didn't buy it because you were able to use the equipment at the school. So why spend another, I don't know, a couple $100 on something that you didn't really have to use? Well, now we need it. So it was decided by others that the labs need to be hands-on, which means some kind of way, I don't know how to lead a lab through a video because you can't see the board. It just has to be figured out. But the point I'm making is you guys need the analog digital trainer. So you need to buy that. I'm going to give you information on where you can get it online. You can get it at the bookstore, but I understand that the bookstore marks them up. So most students, or I have always suggested that you go to another source. So I think Dr. Whaley found a link where they're like $150 or something like that. So I'll be forwarding. You won't need the trainer right now, but you'll need it soon. So I'll give you the information on where you can get it, but feel free to get it from anywhere. I'll give you the model number and the link that he gives me. I'll pass it on to you so you can get the trainer. If you use a different type of trainer, as long as it has functionality for AC, you're welcome to do that too. You can, if you want to, run it past me, you can send me a picture of it and I can look at it and say, yeah, that'll work. If you don't want to use the one that we normally use at the school, but that's the one I'll send you the link to. So you do need that trainer. In addition to the trainer, you need components. You need the resistors and capacitors and inductors and the other stuff that we use. So the way that's going to be handled is the school is going to loan you guys the components. At some point, I don't know when, but at some point in the very near future, when all these packets, these little AC packets are put together, you'll go up and you'll get a packet, you'll bring it home, and you can work with the parts at home. Those packets that they make are on loan to you. They're not given to you to use. They're just loaning it to you. At the end of the semester, you got to take it back because I'm sure they'll charge you for it. So that's something that you'll get from the school. The other thing that'll have to be purchased is a digital multimeter. You can't really do any kind of work without a DMM. Unfortunately, the analog to digital trainer doesn't have a built-in DMM. It would be nice if it did. So you would need a digital multimeter. Now, that's not a really big problem because the multimeters are pretty inexpensive. I bought one, I want to say it was probably at the end of last year. I think I went to Lowe's and spent $20 for one. But I've seen meters as low, literally as low as $5. Now, I wouldn't buy a $5 meter, but I mean, you could. I wouldn't spend over, if you spend $30 on the meter, then it's a really good one. That's like the Cadillac. So around 20-ish, close to $20, you can find a multimeter. Make sure you get a digital multimeter and not the analog one. The analog is the one with the needle that moves back and forth. You want to get a digital multimeter. Now, Dr. Whaley also has a meter that he suggests that you buy. So along with the model number and the link for the analog digital trainer, I'm also going to give you his recommendation on the meter. Now, you don't have to use that one. Like I said, you can go to Lowe's or Home Depot or I get another place, the Harbor Freight. You can get meters all day long at a very reasonable price, or you can get them online. But the nice thing about everybody having the same meter is if we need to talk about some meter functionality, I can point to one thing and everybody knows where I'm pointing to because we all got the same piece of equipment. Although at this point, I don't think it should be a big deal because you guys are now, you've had DC already and you've used the multimeter before. So once you use all multimeters, they're pretty much all the same. Things might be in different positions, but if you understand the device, then you can understand any device. They're pretty much the same. So I'll leave that up to you. I will give you the information that Dr. Whaley gave me to pass on, but I'll leave it up to you as to which meter you get. But I will say you definitely do need the meter. You need the trainer and you need the meter. Another thing that you will need, if you had me before, you probably already have this, you will need a set of coloring pens or pencils. I recommend at least 4 colors. And we did a lot with that in DC, redrawn circuits. We'll do way more this semester in AC. Color coding is important. So you need coloring pens or pencils. I've already mentioned that you need access to a printer or a printer. And then the final thing is you need a way to convert a document to a PDF. So if you have a scanner, you can probably scan a doc. You got to have a way to turn the work in back to me. So I'm going to send you the work to Blackboard, and the way you're going to hand it in is you'll hand it in, you'll upload it to me. And the reason I need it in PDF is because people send me all kinds of documents and all kinds of forms, and sometimes my computer doesn't have what it needs to open up a file. So by changing everything to PDF, it's guaranteed I can open it on any device. So that's the reason I require that. So if you had me last semester, I think Jacob recommended an app, and I didn't get any feedback, plus or minus, on whether that app, people were happy with it or not. But for the most part, I think people used it, and it worked out quite well. So I'll resend that link out, and there was a little YouTube video that talked about it. And if you didn't use that app, you can revisit it. If you have another app that you can take the picture of it with your cell phone and it converts the picture to a PDF, any app that you can use that does that, I'm comfortable with that. You just got to have a way to print out the document, work on it by drawing and doing math on it, and then scan it back as a PDF to me so I can get it and I can grade it. You have to have the ability to do that. So 3-ring binder, analog digital trainer, digital multimeter, coloring pens and pencils, access to a printer, and then a way to convert a file to PDF. Now, with the exception of the 3-ring binder and the 3-hole punch, if you're not able to meet that, if you don't have what I need, then you probably don't need to take the course right now. You probably need to take it later. And I'm not sure when that'll be because this is not written in stone, but they're saying in fall we'll probably, I don't even know if I'm supposed to be saying this, but we'll probably kind of move back to campus, but not fully. That we'll probably still deliver our labs by remote. I mean, our theory by remote, and do the labs up there actually face to face. We can spread out. So that'll change as we get closer to fall. So if you have to withdraw from this course and take it another time, I'm not sure when that'll be. I don't know when we'll be actually fully back in the classroom. It looks like it may be next spring. So we'll have to see how that works out. So I'll help as much as I can. I have a printer here, but it's a long story. I'm not going to go into it. But I was a kid and I let somebody into my computer from India, and they so-called fixed it, and they really fixed it. They tried to get money from me, and I don't know. I'm not going to go into the details of it, but just safe to say, sometimes my printer works and sometimes it doesn't. So, but if I can help, I will. So sometimes I've printed documents for students and done some things, but I don't know how much of that I'll be able to do this semester. The way with them moving the semester to 10 weeks, and it makes our schedules as professors way more busy. I know you're busy, but so it's a little hard to balance things out. But I'll try to make anything work any way that I can assist you guys. I'm willing to do it if I can make it work. So those are the things you need. Again, if the main things, the trainer and the DMM, if that's an issue for you, then you won't be able to do the labs, and you should probably think about taking this course at a later date, maybe when we get back to being face-to-face, which is possibly in fall for the labs. Now, how will the class work? So the class is scheduled, from 1 to 4:20, I think. So now what we'll do is, I'm not going to lecture every day that we meet for that number of hours. You're not going to want to listen to me that long, and I'm not going to want to upload that huge video to YouTube. And so here's what's going to happen. Probably most of the classes will be live streamed. You really need to be here and be involved, because these problems can get kind of detailed, I'll put it like that, and you need to be able to ask questions. So I have a mixed view on videos. On the one hand, I feel like if you put videos up, it's kind of great, because then a student can go, if they did something the first time, they can watch it over and over again until they get it. Or if for some reason you missed the class, well, it's on video, you can go back and you can see what happens. That's the advantage of it. But the disadvantage is that I know I'm putting videos up, and this is not just at Cincinnati State. I work at UC too. In both UC and Cincinnati State, as I start posting videos, the number of people that would attend the live sessions would start to drop off a whole lot. And I'm telling you right now, you can believe me if you don't want to do that in this course, unless you are really good with your algebra, trig, and physics. It can mess you up. So you want to be here. You want to use each other, and if you have to miss, you use a safety net. You can go back and look at the video. But I strongly recommend that you attend this live sessions and go back and review the videos as necessary. But the point I was going to make is the class will probably, I'm not going to start the class at 1. I started at 1 today because I didn't want to confuse anybody. I'm going to start the class at 2 o'clock. And how long it will go, I don't know. It depends on the material. So starting, I think we meet on Wednesday, that class will start at 2 o'clock. And I'm just going to start. So what you got to do is you got to really watch Blackboard, because that time could change. The class is a live web class, but a lot of this stuff you guys are going to have to do on your own. So if you're not one of those students that you're motivated where you can do some stuff without me pushing you, or without the structure of having a face-to-face kind of meeting, then this probably isn't a good class for you. So for the most part, if somebody sends me a message, I can't read it. I see a message, but what you want to do is when I'm done, you can use your mic and you can ask me, because my computer is like far away. I can see something pop up, but I can't read it. So let me get through this, and then I'll take questions. So just hold your question. And if you're calling in, I don't even know if you can ask questions. So you'll have to text, and then maybe somebody can ask me the question. What was I saying? I forgot what I was saying. We're going to start the class at 2 o'clock. And if it doesn't start at 2 o'clock, always at least the day before, I'll send the link out when we're live streaming, and I'll tell you when we'll meet for class. But for the most part, it'll be 2. Sometimes it could be 1. Sometimes it could be 1:30. Sometimes we may not need to meet at all. If I can do some screen recording, it just depends on the nature of the material. So just be aware you need to be engaged with Blackboard and watch the announcements and emails you get from me, so you can get the link and you know when we're meeting and for how long and that kind of stuff. So some of the stuff will be done. Now, I'm willing to, guys, and I don't, if I need to meet you face to face, I'm willing to do that. And when I'm saying that is, I can't do it in any official format like through Cincinnati State, but I know that this stuff can be hard enough to do in person, but when you're doing it through the web, it can make, so if you really, really need to meet me face to face, I can make that happen. Even as a group, if we need to meet at like a park or maybe in the parking lot of the school or something, if we need to meet, we can. We just have to maintain a safe distance and, use a mask to cover and all of that. But if we need to do that, we can talk about that, and that can be made to happen. I would like for, I think there's 8 students. I would like for everybody to get through the class and understand everything and do well. But, a lot of that depends on you. Okay, so that's how the class will work. We will start next time, Wednesday, not at 1 o'clock. It will start at 2, and I'll send the link out sometime tomorrow night. Now, for attendance, what I'd like for you to do is I'm going to put a number on the board. And so right now, your cell phone, and I need you to text me at this number. It's a 513 number. It's 494-6162. So I need you to send me a text. And in the text, put your first name and your last name. And then put EET 132. I need for you to go ahead and do that right now. And if you don't do it, then I'm going to mark you as being absent. And, that's the only way I know to take attendance. So I'll wait a few minutes to give you a chance to text me at that number. Put your first and last name in the text. Put EET 132. That's important because I have like 3 classes and everybody's sending me a text. So when I go through and look at the text, I need to know what class you're in so I can give you say that you were present for that class. And while people are texting me, let me know if you have any questions. Anybody have any questions over anything I asked so far? And I can step over to my computer. If you don't have the ability to talk, I can step over and look at it.
I have a question.
Okay.
Because I'm not even really sure how Blackboard, how it allowed me to do it, but on Wednesdays, I see that this course ends at 4:20, but I also have a course that starts at like 4:10 on Wednesday. And I'm kind of, I don't know now, I guess, because it's just starting with it, but I'm confused on whether like I should be coming there a little bit late, or like will it depend on the lecture? Or
yeah, I think you'll be fine because I will never lecture that late. Your class starts at 4:10.
Yeah.
Yeah, I think pretty much. Now today, I don't know how far we'll get, but I think you'll be fine. If anything, that's Dominic, right?
Yes.
Yeah. First, I'm sorry I didn't get. You asked me for some work to prep you for, and I got so tied up, and I got your.
It's fine. Yeah, I forgot to.
But what I have you do is I don't think you should stay in both classes, and I don't think we'll be going that late, Dominic. But if we do, just sign out of this class and then go ahead and go to that, because you'll just miss the tail end of it if we actually lecture that late, and you can always go back and watch the video. So
Okay.
I don't think that'll be any issue at all. Probably by the most part, we'll be done before then. So that'll work out fine.
Okay.
Yes. Does anybody else have a question? Okay. Let me say one thing. I just got to get this off my chest. Let me say one thing, and then we'll go into the material. So, guys, it was I wasn't pleased last semester. It was just a hard thing. It was hard, not just for me, but for everybody. I know it was hard for students because nobody planned on this. You know, I'm up there, I'm teaching, doing what I've been doing since 1996. I'm happy. The class, all my classes, the students were great, and everything was going great for me. And then just literally one day, they told us that we'd have to go remote. So I purchased the camera. I got all the thing, everything I needed, and it was a little uncomfortable for me, but I had the luxury of the classroom. So even though I didn't have students in front of me, I felt at home in the classroom. I had a big whiteboard, and then we did a couple sessions from there. And then I found out that they was kicking us out of the building, and I really was like a fish out of water. I didn't know what to do. So I don't know if I've ever turned my camera around, but I'm in my basement right now, and I threw this board up. I stole this from the school. I stole a PC from the school. I probably spent close to $1,000. I know it doesn't look like it, just trying to get it up, stuff to where I can go. And then I had to learn how to pass documents back and forth, and um, it's a lot of work. So I just want you to know that when I grade, so I have what I call Blackboard watchers. Blackboard to me is a curse and a blessing. When I was in school, there was no Blackboard. We just kind of knew where we were in the course, and we had enough mathematical knowledge where we can go in and we can do calculations. But I have people that watch Blackboard, and I swear the second I put a grade in, they'll see their grade drop or go up, and then they're calling or texting me. I truly don't even respond to that because the way it works is like this. Blackboard, think of it, the grade book is like an Excel spreadsheet. So on the one hand, I have on the top across the columns, I have the assignments, and on the side, I have the students. And so that cell has to hold something. So you turn in work to me, and let's say that we're on campus. You would turn in work to me, right? And I would take it, put it in the pile, put it in the envelope, I'll take it to my office, and I'll sit there, and it'll sit there until Sunday until I get it. And in a perfect world, if you turn that document in on time, I'll spread all the documents out on the table, and I'll go through every class, I'll grade, and I'll put in something in Blackboard. But let's say you turn it in late, or let's say you emailed it, or let's say it just got mixed up some kind of way. Well, when I'm grading, if your paper isn't there, if it isn't there in the pile with the rest of that assignment, when I'm going through and I see your name, I gotta put something in Blackboard. I can't leave it. It's gotta have a value in there. So if I don't have your paper, what I'll do is I'll put a 0 in there. And the 0 doesn't mean you got a 0. It just means right now you got a 0 because I don't have your paper. Now, if you turn your paper in late, I'll eventually get to it. But if I'm in a certain rhythm, if you get outside that rhythm, you got to wait till I get to it. Well, I get people texting me. I turn that in. I got you don't want to watch Blackboard every day. What you want to do is just kind of, if you see a grade in there, just chill, just relax. And if it over time if it hasn't changed, but you turn it in, then just send me a text and say, hey, I turned that assignment in. I also get students that say they turned something in and they really didn't, and they find it in their notebook. Now I won't have that issue now because if you upload, the only way I'm going to take something is through uploading to Blackboard. So if you upload it, I got it in Blackboard. But please don't. That's not an emergency. Some people texting me on a Sunday, or a time when because you got a 0, and that's not. If you felt like that a grade incorrect, send me a text. But it's not an urgent thing. Or you can ask me like, we'll always have time after a lecture where you can talk and say, hey, check on this and check on that. And I know sometimes I get the stuff right away, but sometimes I don't. Because trust me, I have a long laundry list of stuff that I have to do. But the worst thing you can do is sit there and watch Blackboard and be bent out of shape because your GPA is going up or down. Really, until the end of the semester, it doesn't really matter until the end. And when I have everything, that's what's going to determine, what you get. And I don't give any grades. You guys earn it. I'm a numbers person. I go through. I keep track of what you got right and what you got wrong, and I put the grades in. Now, having said that, I don't really curve, but what I do to benefit the student, what I do is I go through and I download Blackboard Gradebook to Excel, and I ask Excel to round it. So if you got a 79.5, which some people did, you got a 79.5, I had students looking at Blackboard, and they say, man, I got a C. If I just had that half a point, I'd have a B. Well, you really got a B because when I download that, I ask Excel to only show me 2 digits. So what it does is it rounds up. So even though I don't really curve, I guess I kind of do because it's rounded to the next highest score if at least 0.5, 0.5 and above. So I do that. Now, when people are really, really close to a grade, and I get people, was there anything I can do to get my grade? I'm so close to having a C or whatever, a B. Is there anything I can do? Well, what I do is I go back and I look, and there's extra work I give you. Like I might give you a video assignment to watch that, or I'll give you some other work. And when the student asks me that, the first thing I do is I go back and did they turn in this extra work here that I gave this extra credit? Did they do? If I see zeros there, I don't even. You just get what you got, because your opportunity to knock that grade up was taking anything that I give you that's easy, like watch the video or writing a summary or something. That's easy work. Get those points. It counts the same number of points as a really hard quiz grade. So why not do it? So I get a little irritated with Blackboard because, and then you might think you're the only person texting me, but there might be 10 other people texting me. I feel like I'm being machine gunned. So then when I get in my way, I just don't even respond. I say, all right, you'll see. So stay calm. I'm a very reasonable person. I'm not going to screw anybody out of anything. I'm going to give you what you earn, and I really am for the student. If there's any way I can see I can bend or mend them to make things work out in your favor, I'm going to do that. I mean, I've delivered papers to people. You'd be surprised the stuff that I've done to try to make students happy, and I don't think anybody else, and I can honestly say it and feel good about it. I don't think another professor up there will do some of the stuff that I've been doing this past summer to make sure everybody has what they need. But sometimes I feel underappreciated because I get machine gunned, and it's just a whole lot. So I'm saying that to say not to play violins and boo-hoo, none of that stuff. But I just got to be on it this semester. We're using Blackboard. We're uploading assignments to Blackboard. I'm going to give you, this is not an easy course by any means, but I'm going to give you every benefit of the doubt. I'll give you assignments to kind of soften things. And if you really apply yourself, you'll do well. And the good thing about taking a difficult course is when you get through it, then you feel good, and now you know you can handle almost anything. When I was in the engineering school, I did engineering and physics. When I was in the engineering part of it, I think this course was probably the hardest for me. And those are some old schools, real hard engineers. But and I think I might have got a C in it. I don't think I got a B in it. I think I just got through it with a C. But when I started teaching it, I look back at it and I was like, why was this stuff so hard for me? Because I had matured and I had learned many other things that this kind of at least appear easier. So I think if you really apply, and I know most of you, I'm looking in the camera. I know Dominic, I know Jacob. I forget who else is in the class, but I think Tresser. I know most of you. I know you work hard. I think you'll be very, very pleased and satisfied. And if you're doing this stuff, this school stuff, just for a job, okay, it'll make you happy. But if you're like me, you want a job, but you really want to know how did God make this stuff work? How does this thing work? What makes this tick? Well, you're going to be really satisfied because this course will dig into that and answer a lot of that. So I don't want to keep preaching. I want to get into the work. Before we start, does anybody have any more questions? Because we're ready to roll and get the class going. Anybody have any questions or comments? Okay, well, let's get started. What you want to do is make sure you have pen and paper and take notes. And if you have questions, if there's something I have on the board, feel free to interrupt me. Or if you don't feel comfortable doing that, then you can ask me at the end. There will be time for you to do that. Oh, one other thing, since most of the time we'll be starting at 2, that 1 hour between 1 and 2, I don't know if there's some kind of, I know my UC students have some kind of, I don't know if it's a chat room or Facebook, some kind of way where they can communicate with each other. and everybody in the classroom join up. And I'll have to find the name out, but I'm sure you guys know. I don't get into this stuff, but you guys can use that time. You should use some kind of website or some way to communicate with each other, and that time is there for you. You can use that time to communicate. If you can share documents, I know you can share documents through Google Docs, and you can share things, and you guys need to help each other. So when we're not meeting at one, which will be most of the time, it'll be two. But when we're not meeting at one, please use that time to talk to each other, and you should have a buddy up with somebody in the room anyway. But anyway, let me get going because we've been here for a minute. So I want to start by defining something. Everybody knows DC. DC stands for direct current. Direct current. And what that means is that in a DC power circuit, the current flows one way. It flows one way and one way only. And in the DC circuit, the polarity of the voltage is determined by the direction of the voltage source. So if I have the plus side here and the minus sign here, the polarity across everything is plus minus. If I flip it over, then I've changed the polarity of the DC source. But for the most part, the direction of the current does not change, and the magnitude of the current does not change. Now, there is something called pulsating DC. Don't worry about that right now. We'll get to that. If you're an EET student and you take the electronics course, they'll talk about pulsating DC. I might say a little bit about it, but for the most part, there's just DC, direct current. Current flows one way, and the magnitude or value of the current does not change. It stays the same number of amps. It does not change. Whereas AC, what we're going to talk about this semester, AC stands for alternating current. So here, the current goes one way in the circuit, and then it goes the other way. And it goes one way, it alternates back and forth. And not only does it alternate back and forth, but it does that at a regular time. We say it's periodic. If something is periodic, it does it at a regular time. So we got the current that goes back and forth. And not only does it alternate back and forth, that current also changes in magnitude. So it starts at 0 amps, it goes up to a maximum amount, then goes back to 0, and then it changes direction and repeats that process. And so that's the way AC is. So one question we want to answer is, well, why is that? Why is it that this is periodic? Why is it that it goes up, it starts at 0, goes to maximum, goes back to 0, and then changes the direction? Why is that? Why does it work that way? And this is when I said that I teach from first principles. You take anybody else's course, what they're going to do is they're going to go into AC, that'll all be skipped over, and they'll go right into the AC math stuff. But I want you to understand what's under the hood before we drive the car. So you'll understand that. So there's two types of current. There's DC, direct current, and AC, alternating current. And so the question I want to ask is here, why do we have DC and AC? What's the purpose of having two? Is there a way to get away with just one? And the answer is, yeah, we could get away with one. We could get away with, matter of fact, back around the time of Edison, the only thing we had was DC. There was no AC. AC didn't come along. There was this guy named Nikola Tesla. Some of you might know the name. He is responsible for bringing this on board. Tesla and Westinghouse and those names might mean something to you. But before that, it was Edison and DC. Thomas Edison had the whole country wired up with DC. And then Tesla came and said, well, you know what? I got a better way to. Remember, even though we talk about current, we talk about voltage, but really what we're moving, we talk about power, but really what we move is energy. And so what Tesla said, he said, Mr. Edison, you're moving energy this way. I got a better way to do it. I can move it this way, and it turns out moving it this way is better. But I want to know, I want to answer why is it true that this is better? So first, why do we need AC and DC? Now, here's the answer to that. Partially is the document that I need for you guys to look at on Blackboard. There's a packet, and that packet shows you an AC power distribution system. You need to look at that document. I think what I'm going to do though is I'm going to actually make a little video of that, and I'm going to talk about that document. Since I can't hold it up in front of the camera, I'll make a little video. I'll record my screen, and I'll say something about that document to help you understand what I'm about to say now. But here's the thing. If you remember, if you had me for DC and you had me for lab, you'll remember that we talked about the resistance of wire. And you might remember this formula. R sub W equals rho L over A, where R sub W is the resistance of wire. This is the resistance of wire. Wire resistance. This right here is just a constant, resistivity. We don't really have to worry about constants, because what that is a characteristic of the material. In other words, if I have, let's say copper, it'll have a certain value for resistivity. Not resistance, but resistivity. So all copper would have that same value, but if you go over from copper to aluminum, it's constant for aluminum, but it's different from copper. So I don't really have to really say too much about that. Pretty much we use copper, but that's just a constant. This is, of course, the length, and this right here is the cross-sectional area of the wire. So let's roll back to the time of Thomas Edison. Edison was born in the 1800s, and he's responsible for a lot of different things, you know, the light bulb, but he's actually the phonograph, a whole bunch of stuff that the man invented. He was really a genius. But at the time of Edison, he had the country wired up with DC. So there was a way that they would actually make or generate DC, some kind of a battery. They would use DC to power the telegraphs and lights and whatever they had back in the day. So let's say that the power station is here. This is the power. I'll just put P for power. And the house is over here. And what you got to do, this is DC power. So this is DC. You got to run a power line from here to the house. And so you can see, just by looking at this formula, look at the relationship between R sub W and L. There's a direct relationship between R sub W and L. The resistance of wire is directly related to the length of wire. So if I have a power generating plant over here, and many, many, many miles away, I have the city or the town that I'm trying to distribute the power to. If I have a really long piece of wire, that means the resistance of that wire is going to be really high. Now that in itself is not a problem until you run a current through it. If I take resistance and run current through it, well, a couple things happen. I get a voltage dropped across the wire. If this is really, really, really big, then that voltage drop across the wire, when I multiply I times R, it's going to be really, really, really big. So your voltage is getting reduced over here. But really it isn't the voltage that we're worried about. It's the power. Now remember, what power is energy per unit time. So how fast are we delivering energy? So instead of multiplying this by I, if I multiply this by I squared, then what I'm getting over here, the left side of the equal sign, is not voltage anymore. Now it's power. P is I squared R. That's a form of Watt's law. And look at this. If I have a really high wire resistance, then I'm going to have a really high power, but that power is dissipated in the wire. We don't want that. We want the power over here in this house. All that power is dissipated right here. And so if the power is dissipated where you don't want it, then we call that power a power loss. So by having long wires distributing power throughout the city, there's a huge power loss. So Edison's system worked. It's better than nothing. I mean, before that, they had candles. So his system was better than a candle, but it wasn't very efficient because of this relationship between R sub W and L, causing great power loss. So the genius Nikola Tesla, he looked at this problem. He said, you know what? I think I can get a way around that. If we don't use DC, if we use something called AC, the man really was a genius. It was once said that Dr. Albert Einstein, somebody asked Einstein and Tesla lived around the same time. And so somebody asked Albert Einstein, hey, Einstein, professor, how does it feel to be a genius? And Einstein replied, I don't know, ask Nikola Tesla. So when you have arguably the smartest man in the universe, in the world, Albert Einstein, paying homage to Nikola Tesla, he said, I'm not a genius, that man's a genius. Then that's a big thing. So Nikola Tesla was really a sharp cookie. He really was. He could see things that other people couldn't see. He was able to see beyond this. Edison was an experimentalist. A lot of his inventions came from just trying things over and over and over again. It was said that he went through 1,000 filaments for a light bulb before he found the one that wouldn't burn up. And it was like, Edison, you're really wasting your time. You went through 1,000 filaments trying to figure out the one that works. And Edison said, I didn't waste any time. I just found 1,000 ways not to make a light bulb. So it's kind of funny. But this man Tesla could see beyond this. The thing that you can do with AC that you can't do with DC is you can use a device called a transformer. Now, we're going to talk about transformers, but I'm not going to do it right now. I'm just going to show you something real quick. A transformer is a device that we can use. It only works with AC. We can use this to make an AC voltage bigger or make an AC voltage smaller. So you've all seen transformers before. You might not recognize it as a transformer, but if you go outside and look at your telephone pole, if you have a telephone pole outside your house, you might have a telephone pole, and then there's a big gray cylinder up there, around like a big cylinder, and usually there's 3 wires coming from this over to your house. Here's your house. You got 3 power wires coming over there. Well, that's a transformer. Also, if you have a charger, and I'm not talking about a USB charger, but the kind of charger with the plug on it, you plug it in the wall, and then you plug your cell phone into that. The thing that you're plugging in the wall is a transformer. We'll go into detail on transformers because they're very important and they're interesting, but transformers don't work with DC. They only work with AC for reasons you'll understand later. So, but the thing about a transformer, what you can do is you can make the voltage bigger. I can make it, for all practical purposes, as big as I want it, or I can make it smaller. So when you take a transformer and you make the AC voltage bigger, you call that a step-up transformer. If you take the transformer and make it smaller, you call that a step-down transformer. And so it seems like, if you follow what I'm saying, it might seem like that you're creating something from nothing. So hold on, Ron. Are you saying I have this transformer? Let's say I have a transformer, and I'm sending AC into it. So here's my transformer. Now, when engineers write out, sometimes they don't spell that whole word out. They'll use an X for this, and they'll call it an X-former. So I'm going to do that here. This is my transformer. It's just a shorthand way of writing transformer. And in here, maybe I'm sending 100 volts of AC. So I have 100 volts AC. Well, if this is a step-up transformer, step up, I can step this voltage up to whatever I want. Maybe I step to 200 volts AC. And you might look at that and say, well, hold on a second. That don't feel right to me. It looks like I'm getting something from nothing. Imagine putting $100 in the bank, running it through a box, and it turns into $200. You know, nature doesn't work like that. It's impossible to get something for nothing. I can't create voltage. Well, you kind of can create voltage, but it's always at the expense of something else. So here's what really happens. You can raise this voltage up or down. You can make a step-up transformer or step-down transformer. But what has to be true is this. whatever power goes into the transformer is what comes out. Now we're assuming we have an ideal transformer. So for a transformer, an ideal transformer, the power that goes in to equal the power that comes out. So as long as that's true, then you can raise and lower the voltages up to whatever you want. Doesn't matter. But the only way to do that and make this true, let's say over here I put in 2 volts and I put in 2 volts and 6 amps. Well, if I put in 2 volts AC at 6 amps, then my power is B times I. My power is 12 watts. So I'm allowed to step the voltage up, but I still got to have 12 watts on this side. So let's say I step this up to 4 volts. If I step this up to 4 volts, I can have 4 volts over here, but then that means that current has to drop down to 3 amps because the product of these has to stay the same, 12 watts. This is a result of the conservation of energy principle. Even though I'm talking about power, what we're really talking about is energy. So energy in equals energy out, but we're doing it in terms of power. So since power has to stay constant, you can make the voltage bigger or smaller at the expense of the current. If I step the voltage up, the current's going to go down. If I step the voltage down, the current's going to go up because the power has to stay the same with this device called a transformer. Well, Tesla seen that. He was thinking about that and said, got an idea. What if we did this? What if in my city I have an AC generator? So I have an AC generator in my city. I generate the AC and I run that AC to a step up transformer that makes the voltage really high. Then on the other side of the step up transformer, here's the long wire, the same long wire that Edison had. I have this really, really long wire. And then over here I go to another transformer. This is a step down transformer. And then from there I go to the city or town, or here's my house. Now let's look at this. Now what happens is I generate this AC, but right here I step the voltage up. So the voltage goes way up, which means the current goes way down. Right? Well, remember power law as a system? Power loss was described by P loss equals I squared times R sub W. We really can't change that R sub W because remember R sub W was directly related to the length of the wire. So we can't make the city and the town closer together. Once this is built and that's built, R sub W, the length is what it is. Now what you could do in the formula, R sub W is actually inversely related to the area of the wire. If you remember the formula, R sub W is rho L over A. So R sub W and the area of the wire, they're inversely related. So one thing I could do to fix this, Tesla could have said, you know what we can do? We can get a bigger area wire, a thicker wire, and that'll knock our resistance down too. So I can lower the resistance down in this formula. But what's the problem with that? The problem is if I get a thicker power distribution wire, first of all, thicker wire is going to cost more money. Secondly, the structures. You got to support that wire when you run. If you ever drive up the highway, not the expressway like 70. I mean, you're out in the boondocks on the highway. You see those huge power distribution towers, and those wires they look thin, but they're really thick copper wires. They're draped from one tower to another. If I get heavier wire, the wire's going to cost more. I mean, if I get thicker wire, it's going to cost more. Those towers that support it's going to cost. All the costs are going to scale up. So getting a thicker wire, increasing A is not a solution. But Tesla said, well, if I step the voltage way up, then the current goes down. And in this equation, look what happens. If I send the current down, because I'm squaring that number that drop is squared, it really has a drastic effect on reducing the power loss. So here's what they do is they make the AC, they send it to a step-up transformer, they step the voltage way up to like a 500,000 volts, and that makes the current really low. They transmit power at a high voltage, low current. If the current is low, the power loss in the wire is low. When they get the power where they need it, now they reverse this process. They send it to a step-down transformer, bring the voltage back down, which means the current goes up, and now that power can be delivered over here without significant power loss. So remember I said earlier that you've seen transformers before? If you've seen a telephone pole, and it has that cylinder on it, that big ray, looks like a big tin can, and then you have your 3 wires coming out of there. Here's your house. Then you have your 3 wires coming out of there. That is a 2-phase step down transformer. That's a step down transformer. So this steps it down from, I forget, on this side of the power lines. I want to say it's about 2,000 volts. I might be off a little bit, but it's a relatively high volt, like 2,000 volts. It steps it down to 220, 240 volts AC. And then from that, in the house, they can split that 240 volts divided by 2 is 120 volts. They can use half of that. You know, your wall outlet puts out 120 volts. Well, the reason is they take this 240 and split it in half. Now, you might say, why don't they just step it down to 120 right away? Why step it down to 240? Well, the problem is some machines, like you might have a stove, or I've seen dryers that require 220 volts or 240 volts because they run more efficiently at a higher voltage. So you might need the 240 for some other device. They bring it in at 240, and then they can break it off, and you can, for your wall outlets, they can and your lights can be 120. But if you got like a dryer or stove at these 240, they can get it off that. So that's the reason we need 2. You got to have AC to distribute the power efficiently, and then DC to run the equipment whatever it is we're trying to power over here. You might say, well, hold on a second, Singleton, then why don't we do this to eliminate one of these? Why don't we just do everything in AC? Why do we got to have AC to distribute power and then DC to run stuff? Why can't we just have the AC run everything? That way we can eliminate DC altogether. Well, the reason you don't want to do that is you can design devices. Like I can design, your cell phone is a DC device. Even though you get into the wall to charge it, it's DC. You can unplug it and it'll still work because it has a battery in it. If it has a battery in it, it's DC. So you can make that same cell phone AC. I can make an AC operated cell phone, but the circuitry for an AC operated cell phone will be magnitudes of an order more complicated than a DC. Using DC current and voltage to design devices, the devices are much simpler. So what we do is we generate it as AC, and what I want to do is talk about what goes on in that box. How do we generate the AC, and what does it look like? We generate it as AC. We step the voltage up with a step-up transformer real high because the current will drop, and then I can send it across the power line at a low current, which makes the power loss in the wire very, very low. And so it's more efficient to transmit the power over to where I want it. When I get the power where I want it, I step it back down, which brings the current up. So now I got that power over here that was transmitted very efficiently. And then when you take your cell phone or computer and plug it into the wall, you're thinking it's AC because I'm plugging it into an AC outlet, but that's not true. You plug it into an AC outlet, but there's a circuit in most devices called a rectifier circuit. And the purpose of that circuit is to take the AC and change it to DC. So right now I'm looking at my laptop over there. It's plugged into the wall, And you might think it's AC, but I can unplug it and walk away with it because there's a battery in it. So most devices are DC. Now there's some AC devices like a vacuum cleaner motor is probably straight AC, but most devices are DC. Even if they plug into the wall, the circuit inside of it called a rectifier that takes that 120 volts of AC and converts it to DC. And if you're an EET student and you take the electronics class, or even if you're not an EET student, you're like electromechanical, and you don't take electronics, I highly recommend you take the electronics class because there they explain that process of rectification and how to do all of this. So it's kind of cool how they do it. So again, there's a packet on Blackboard that goes into this power distribution system. I think what I'm going to do is I'll make a screen recording of that, and I can talk about. You can see the power distribution systems. They got the proper voltage levels. I just made the numbers up, but they got the proper voltage levels in there. You'll see the step-up transformers and the distribution system, and you'll understand it a lot better if I go over it. So I'll make a screen recording of that, and I'll talk about some of the stuff in that package. So that package is actually pretty important for our whole conversation today. So, boy, that's a long explanation, but that's why we need both AC and DC. You got to make sure you can answer that question. Why do we need both AC and DC? Well, we need AC because it's more efficient to transmit power, to move energy from one place to another in the form of AC. Why? Because I can step the voltage up, which knocks the current down. I lower the current, I lower the power loss in the wire, and I can bring the voltage back up when I need it. We need DC because it turns out that when I'm designing devices, I have a choice to make this device an AC device or a DC device. The DC device will always be simpler to design. It's just the nature of the beast. And so I actually need both. AC, the power to move the energy from one place to another, and DC to actually run whatever device we're talking about. Now, there may be some other side reasons, but those are the main reasons why we have AC and DC. So I spent a lot of time explaining that, so that must mean it's important. Well, most people skip that part of the class, but I want you guys to see that because I think you can appreciate that. Now you can see why we need both. Now, does anybody have any questions over what I talked about? Any questions you want to ask me before I move to the next point?
You said DC is easier to run?
The DC?
Yes.
So with DC, what I said was, if I'm going to, let's say I'm going to, excuse me, I'm going to design a device, a widget. We'll just call it a widget. And as an engineer, I have a choice. I can make the widget work off a DC or AC. I can design it either way. What I'm saying with most devices, all other things being equal, if you design it to use DC, then the device is usually simpler to design. Usually. Now, that's not true with some type of motors, but for the most part, if I design your cell phone to be strictly AC, well, that'll be a mess because you always have to have it plug in. It wouldn't be very portable, but I could do it. I can make it straight AC, but the circuitry inside of it, which is already complicated, will be even more complicated. So all things being equal, if I could design a device to work off either AC or DC, my design will always be simpler if I design the device to work off DC. So that's the reason for that. Is that it?
So you can't have a AC, this is Randy, by the way, you can't have an AC battery? It's just DC,
No.
right? Okay.
Yep. Matter of fact,
This is Randy.
Who was it?
Randy.
Randy, okay. Randy, I'm glad you brought it up because, no, you can't have an AC battery. But I do want to talk about how do we get AC? How do we get AC? How do we get this? So on Blackboard, there's a document. I don't know what I titled it, but when you open it up, it talks about the 4 ways to get AC. So I want to talk about some of those. If I can erase this, since Randy brought it up. You can't have DC, a battery. What does a battery do? A battery separates charge. If you remember our discussion on batteries back in DC, I showed you charge being separated. It creates an electromotive force between the separated charge. If you put charge in that electric field that's free to move, it's going to move in one direction. That's DC. Well, it turns out in AC, there's a couple different ways we can create AC. So let me talk about that. You can't do it with a battery. Battery is only DC. Well, I shouldn't say that. You can't do it with a battery by itself. But if you add another part to a battery, you can do it. But I'll get to that in a second. So I don't know why I coughed down here. It must be something in my basement. It's getting in my throat or something. All right. Okay, so there's a document on Blackboard that talks about, I have, let's see, 1, 2, 3, 4, 5 ways. I said 4. 5 ways to create AC. So I'm going to put it on the board, but you guys should look at that document because there's pictures there. I think anytime you have words in the picture, it just makes stuff more clear. So let me list these out real quick. Then we'll talk about them. So one way to make AC, this is ways to make AC. So one way, I'll just put number 1. One way is a generator plant. Okay, so that's like Duke Energy or whatever your power company is. They use a generator plant. And when you look at that document I'm talking about on Blackboard, you'll see a generator plant. Now these generator plants can be, the one that we use around here is coal operated. They burn coal. But it can be powered different ways. So we'll get into some details of that. But one way is a generator plant. Another way to get AC is a portable generator. So it's like a little one of these. So I had a buddy that bought a box truck. A friend of mine bought an old ice cream truck, and he drove to these apartment complexes where there wasn't a lot of stores around. He actually had a little store on the truck. Everything you can buy, not everything, but you can buy a lot of stuff that you would go to like a UDF or something, and he just had this stuff. We would drive up into the neighborhood, park the truck, and he could sell items out the side of the truck. But he had a little generator he would start up, and it would provide him with AC. And he could run a refrigerator on the truck to keep the ice cream cold. He can do whatever. So it's a portable generator. So it's like a mini one of these. Another way, a very popular way, or becoming more popular, is wind power station. A wind power station. So they got one of these over in Eaton Park. You probably never notice it, but if you're going, you can probably see it when you're coming, I think going up Gilbert. You look over to Eaton Park, in the tree line over there, you'll see a wind turbine. You got a wind turbine over there powering something. So one kind of way, another kind of way is a wind power station. Another way you could do it, create AC, is a solar panel. Now let me say a little bit about something. The solar panel, actually, you cannot create AC with a solar panel. What happens with a solar panel, the sun irradiates this, and when the light hits the solar panel, it knocks electrons off, and it causes the charge to separate. And you know a separation of charge is a voltage, but the way they separate, this actually gives you DC voltage. So this is DC voltage. But what you can do with this solar cell, this is a solar cell, a solar panel. What you can do with the DC voltage, you can run that to something called an inverter. And And the inverter will electronically take that DC current, change it to an AC current. So you DC in to the inverter, and what you do is you get AC out. Now you might have heard of an inverter if you have a camper. I don't know if anybody has, if you're rich enough to have a camper or a what you call motorhome. A lot of those will have inverters in them. They'll have a big battery under the hood, and connected to the battery is a circuit called an inverter. And that allows you to take the DC voltage from the battery and flip it over or change it over to AC electronically. And the same thing, if you put solar cells on your house, sometimes you see solar cells on the roof. Well, all that energy collected is put out in the form of DC. In your house, you know, it got to be AC. Your wall outlet requires AC. So on the solar panel for your house, you got to have this inverter to convert the DC to AC. That's not an easy process to do, but these inverters are pretty efficient. So I can do it with a solar panel as long as I have an inverter, because I want you to know that a solar panel by itself can only put out DC. It cannot make AC directly. And then the last thing, or the last way, is something called a function generator. The function generator, I don't think it has any practical application other than in lab. So when you, in lab, the way you get AC in lab, you know, in DC, when we did lab, we had the DC power supply. You probably never noticed it, but there was actually an AC power supply there called a function generator. It had a knob and some radio buttons on it. And we never talked about it because it wasn't part of the course. But you can also, electronically, you can get AC with this function generator. So it does it electronically. Now, I said that twice. I said the word electronically for this inverter and for the function generator. And I'm saying that for a reason. Electronically, which means that you're converting DC to AC and there's no moving parts. It's all done with resistors and capacitors and things that are passive. There's no moving parts. But for all of the other ways I showed you right here, all these ways, they have something in common. Does anybody know, if you think about a generator, a big generator plant with a big generator in it, a portable generator, or a wind power station, which is just a generator powered by wind, does anybody think of what do these three have in common?
Probably a moving turbine.
Yes. Who was that, Jacob?
Yeah, it was Jacob Roush.
Well, Jacob said, Jacob Roush. I thought it was Roach.
No.
I'm just, I like calling Jacob Roach. But yeah, he's right. The fact that he said everything is a moving turbine, but even more than that, the way it moves it's what we call a rotating machine. Number one, the generator in the generator power plant, the portable generator or the wind generator, to get them to work, they all have to rotate. It's a rotating machine. And because of that, that gives us AC, but AC of a certain form. So I want to dig into that and I want to talk about that. It turns out that that's very important. Jacob, that was a good call. That's exactly right. So we call these three rotating machines. Rotating machines. And the reason why that's important is because when you make AC, there's actually three forms of AC, three forms of alternating current. Let me draw them for you real quick. Let me show you what AC looks like. So I'm going to get rid of this and show you the three forms of AC that you can have. I can have AC that looks like this. And it keeps going. I can have AC that looks like this. and it keeps going. Or I can have AC that looks like this. And it keeps going. All three of these waveforms are called waveforms. They're all AC. This one right here is called a triangle wave or sawtooth, but it's AC. This one right here is called a square wave. But it's also AC. The current is alternating. It's changing. And this one is AC, but this is called a sine wave. So all these are different forms of AC, and your device won't work with all of these. It only works with one kind. So it turns out that a rotating machine can only produce one of these, and the one that it will produce is that one. We call that sinusoidal AC. And what I'm going to attempt to do, I don't know if I have the energy or we'll see, is to explain, okay, of the three forms of AC I can have, why is it that when I have a rotating machine, it looks like that and not like that or like that? I want to explain that, or attempt to explain it through this camera, which is going to be interesting because I can pull it off at the school with my pictures and all of that. We'll see how well I do. So there's three forms of AC, but only one form if I'm generating that AC with something that rotates. Rotating machines always make AC like this. Now, if I have a function generator, or if I do it electronically, like with an inverter, I can make this kind, or this kind. Matter of fact, if you're in the lab or go to your multi-sim and you bring up the oscilloscope, speaking of lab, there is a lab. Don't let me forget to tell you what the lab is. There's a lab assignment. There's not really a lab. So I'll have to, hopefully I don't forget to tell you that. But if you're in the lab, there's a function generator. You can see I can set a knob to triangle wave AC, square wave AC, or sine wave AC. I can set that. You can go to multi-sim and see bring up the oscilloscope device, and you'll see this, or that. I can have a choice. But if I have a rotating machine, a generator, the only kind of waveform it can produce directly is that. If I want to get this or that out of a generator, a rotating machine, I got to do something else to it. But what comes out of the machine itself is that. So this is kind of special because this is the waveform that we use for reasons that I'll get to in just a second. Okay? So let me talk about that. Anybody have any questions over this AC right here? Let me talk about the generator. Now, this is the part of the class where if we were meeting, I would show you a video, and you've actually seen the video before. I showed you a video when we talked about magnetism. If you remember, if you had me for DC, and I'll send you the link to the video because I know some of you didn't have me or you might have forgotten the video, but I want to remind you of something. I showed you a video where there was a guy who had a coil of wire, actually had 3 coils of wire. He had a coil that had 1 loop of wire. He had a coil that had 10 loops of wire. He had a coil that had 100 loops of wire on it. And what he did is he took the wire and the magnet, he hooked the loops up to a meter, a current meter. And the current meter was interesting because most meters, the needle will park either over here or park over here. Well, in the meter he had, the 0 was right there. And so the needle can move to the left or to the right, indicating the direction of current. And what he had was he had a loop of wire, and he hooked that up to the meter. And when he passed the magnet through the wire, the needle moved a little bit and then stopped. When he pulled it back, it went the other way and then it stopped. And if he moved it back and forth, you would see the needle move back and forth a little bit, indicating that the direction of the current is changing. It's alternating back and forth, depending on the direction that I move the magnet through the coil. And then he said, okay, what if I go from one loop to 10 loops? And what you saw when he added more coils, more turns, you got that same alternating effect depending on the direction of the magnet through the coil, but it was more current produced. And then he went from 10 loops to 100, and he did the same thing, and it really alternated back and forth. What he was trying to show you was the more turns I have of wire, more loops I have, the more voltage I create, the more current that voltage will make, and that's going to be AC in nature. The other thing he did is he moved it in real fast and moved it out real fast, showing that the speed at which you move the magnetic field across these wires also can affect the amount of current produced. The faster you move it, the more current produced. So there was a topic we talked about, and I want to remind you of it, called Faraday's Law, because that's what that was a demonstration of. Faraday's Law. Faraday. And I'm going to send a link to that video out again so you can review that, because you might not remember it. But Michael Faraday said that you can induce or create a voltage if you have a coil or conductor. Got to have a conductor or coil of wire. I got to have a magnetic field. And I got to have movement between the magnet and the coil. If you have that, you create a voltage. We call it an induced voltage. So I can take a coil and a magnet and do this, and I can create energy that flows back and forth depending on which way the coil goes through the loop. Now, I mentioned when I showed you that video, there's a couple devices based on Faraday's Law. If you ever had a flashlight, and I might even brought one of these into the classroom. Let me see if I have one. I think I got it upstairs. If I got a flashlight, I can just shake it, and it'll charge up a battery. And I can use it as an LED flashlight. And what's in that flashlight is I got a little LED light bulb in there. There's an LED light bulb. There's a tube. There's a tube, and in the tube, there's a magnet in there that's free to move. And then around the tube, there's a coil of wire. And this runs over to either a capacitor or a rechargeable battery. And so what happens is I can shake this, and as I shake it, that magnet moves up and down and cuts across the coil, and I'm turning the mechanical energy of my arm, moving up and down, into electrical energy that's stored in the battery. And turn the LED on, then this energy will flow and light it. Or you might have seen a radio that you can crank up. You can turn a crank to charge it, and then you can listen to your radio. That's all based on Faraday's Law. If I got a moving magnetic field that cuts across a conductor, then those electrons are forced to one side, creating a voltage. But unlike a battery, they're forced to one side and then the other side, and you create voltage, but voltage of an AC form. So I want to go into that. I think I can do a good job explaining that. But I want to show you why. Remember what I'm trying to ask, or what I'm trying to answer is, why is AC looking like it? Why is it the sine wave? Why is it the sine wave? Well, and at any point, guys, if you need to ask a question, please interrupt me. So we're going to drill down into this a little bit deeper. And I don't know how long I'm going to, before I run out of gas today, but we'll see how far we get through this. So I'm going to show you a basic generator. This is a basic generator. All you need is a couple magnets, Here's a North Pole magnet, and here's a South Pole magnet. And you gotta have a conductor. So here's my conductor. So maybe that's a copper pipe. Or a copper wire. I got a piece of copper. If you remember when we talked about magnetism in DC, that magnetic field is actually a group of flux lines. Flux. I'm saying flux. And that flux has direction from north to south. So I got magnetic field moving like this. Right? Now, let me show you an analogy here. I'm gonna move away from electrical stuff for us, and I'm gonna make something up, and I want you to understand what's going on here. Let's say that I have, let me get rid of this pipe. Let's say I got those two magnets, and I'm going to get another magnet, a little bitty magnet. Let's say I got a magnet here, a small magnet with the North and the South Pole. And what I want to do is I want that North Pole. So I get a saw, and I saw this magnet in half. Because what I want is that North Pole. So I want the North Pole and South Pole to be separated. So I want to be able to have a North Pole and the South Pole. The problem is, you're probably knowing that ain't going to work. Because if I cut a magnet in half, then what I get is two smaller magnets. I get a North and the South here, and a North and the South here. And if I cut these in half, I just get smaller and smaller magnets. But let's just play around. Let's say it was possible to do this. Let's say it was possible to get a North Pole, a magnet, cut the North Pole out, cut the South Pole out, so I can have poles separated. And what I'm going to do is I'm going to have those two poles, magnetic poles, and another piece of metal that's not magnetic at all. So I'm going to take this and move it over here. So I got a North Pole, I got a South Pole, and then I got another, I'll just do it like that. I got another metal that's non-magnetic. Okay? And then to make this even more interesting, you see how I have these square magnets? I'm going to shade these so that they're round, because I want these to look like balls so I can roll them. So I got these poles, I'm going to foul them off so they're round. So I got a North Pole, I got a South Pole, and I got another metal ball that doesn't have any magnetic polarity at all. Let's say I could do that. And now this is on the table, and you're looking down at the table. You can see I got a North Pole here and a South Pole here. And I got these magnetic balls. Let's call them magnetic balls. I got one that's a North, one that's a South, and one that's no magnetism at all. And what I'm going to do is I'm going to just hit that and let that roll. Let me get a different color pen. I'm going to let this roll. This is going to roll into here. And when this rolls into that magnetic field, what's going to happen is, since that's a North Pole, it's going to get stuck right there. And when the South Pole gets in here, it's going to get stuck right there. But this one, nothing's going to happen. When it goes through, it's going to go all the way through because it has no magnetism at all. It had no magnetic polarity in the beginning. These are going to get stuck. It's going to move in a straight line, but then it's going to be forced down, sideways down. And this is going to move, and the South and the North, they're going to attract, it's going to be moved up. But let's say that I do this, I move that in there, but I do it really hard and really fast. What might happen if I do it hard enough, instead of moving in here and getting stuck on that South Pole, what will happen is this thing will move in a straight line, and as soon as it gets in here, it's going to be pulled down that way. But if I do it fast, I might miss that magnet and have this come out over here like that. The point is, as long as that magnetic polarity is in that magnetic field, it experiences a downward force. If it wasn't, this would go in a straight line. And the same with this. I have a South Pole and a North Pole. If I'm moving it really slow, it's going to get stuck to the North Pole. If I hit that, move it fast enough, then what will happen is it'll move in a straight line. And then when it gets in there and starts to feel the upward pull of that North Pole, it's going to feel a sideways force up that way. If I do it fast enough, I might miss that magnet and actually have it go that way. So now I have the south coming out here, north here, and the one with no magnetic polarity coming straight through. That's what will happen if I can isolate a North Pole, isolate a South Pole, and I have some that with no magnetic polarity at all. If I could do that, that's what that would look like. Well, guess what? It turns out we can actually do that. I can have an isolated South Pole. I can have an isolated North Pole, and I can have a particle with no magnetic polarity at all. You might say, well, hold on, how is that possible? The answer is the subatomic particles. You might say, well, hold on a second. Why are we talking about subatomic particles? Well, we've always talked about subatomic particles. If you remember in DC, we talked about the atom, didn't we? When we started our study of electricity, we started by talking about the atom. And we know the atom has a nucleus, and in the nucleus we have protons and neutrons. And going around the nucleus of the atom, we have electrons, right? Well, it turns out that if I take an electron and I park it right there, there is a field that moves out in every direction called an electric field. The same is true of the proton. If I have a proton here, and actually I should draw these arrows the other way. If I have a proton here, there's a field that moves out, but actually I should draw the field lines going in, but don't worry about it. You get the point. But if the field lines on the electron was like this, and on the proton, they will come in this way. It doesn't really matter. Know that there's this field that exists around the electron and the proton called an electric field. But the neutron doesn't have any field around it at all because it does not have the property of charge. This has no charge, so there's no electric field. Only things that have charge have electric fields. And the only difference between the electric field of an electron and a proton are the direction of the field lines. And I actually have these reversed, but again, it doesn't matter. So, the interesting thing is, and scientists don't know why this is the case, but here's what happens. If I have a charged particle, electron or proton, not the neutron, they're not charged. If I have a charged particle, it has a field called an electric field. If I move that charged particle, I still have the electric field, but as long as it's moving, I also have a magnetic field that appears around that particle. We don't know why, we don't know how. All we do is observe the physics, observe what happens, and we describe it. So any moving charge is going to create a magnetic field. And you kind of already know that from DC. You know from DC that if you have a wire and current flows in that wire, you can use the right-hand rule, and you know that there is a magnetic field that exists around that wire that's created by the flow of charge, the flow of electrons. So if I move electrons through a wire, that magnetic field is created because I have charge in motion. Anytime you have charge in motion, you got a magnetic field. But the thing about it is, if, let's say, the electron acts like a North Pole when I move it. If I stop moving it, I still have the electric field, but the magnetic field will disappear. I only have that magnetic field when the charge is in motion. But the point I'm making is, if the electron acts like a North Pole, then the proton is going to act like a South Pole. Or if the electron acts like a South Pole, then the proton acts like a North Pole. I don't really know which it is. It doesn't really matter. The only thing that's important is I have two poles. If I have an electron and a proton, when they're moving, one is going to have north magnetic polarity, and the other is going to have south magnetic polarity, and the neutron is going to have no magnetic polarity at all. Now remember what current is. Current is charge in motion. So instead of having magnets here, what I could do, if I wanted to, I can take these subatomic particles. I can take an electron and put here. I can take a proton and put here. And I can take a neutron and put here. And that neutron, since it has no charge, when I move it, will not develop a magnetic field around it. So what it'll do, it'll go straight through. However, electron, let's say when it's moving, it has a magnetic polarity of a north pole magnet. It's going to move in and get sucked down, because anytime it moves through the magnetic field, the flux lines, there's going to be a sideways force acting on it. It's going to be pulled down. But if I move it fast enough, it's going to move through and not hit that magnet. The electron will come out over here. And if the electron is pulled down, because it's negative charge, it's going to have a certain magnetic polarity. Then this is going to have the opposite polarity and be pulled up. So the proton would actually end up here if I moved it too fast enough. Now this is actually very, very interesting, because they actually have machines to do this. In some physics labs, they have these big circular tubes that they use to accelerate particles, and they smash them into each other, and then the physicists will look to see what comes out. Now, it's always interesting when they say they'll look to see what comes out, as if they can see these subatomic particles. They can't really see them, but they have sensors and devices that can measure them. And this is one way they use to separate subatomic particles. If I know what I have going in, if I know the magnetic polarity of the electron, and I know the magnetic polarity of the proton, and I know the magnetic polarity of the neutron, which is 0, then over here, I know if I have a sensor here, and a sensor here, and a sensor here, I know that what has to hit the sensor here will be proton. If I know the magnetic polarity is the south pole, it's going to be towards the north pole. My sensor will pick up protons here, electrons here, and neutrons will come straight through. So scientists actually use this to separate subatomic particles. Now, I'm really dumbing this down, making it really simple, but it's a complicated device. But the physics is actually pretty simple. This is the way it works. Now, okay, well, what does this have to do with AC, you might think? Well, let me show you what it has to do with AC. The takeaway from this discussion is this. If I have a charge moving through a magnetic field, there's a sideways force acting on it, as long as that charge is in the magnetic field. So when I'm moving this thing was pulled to one direction. And this was pulled, but notice when I got outside of the magnetic field, now it's moving in a straight line again, because it's not being pulled down and pulled up. There's no more force on it. So let me, I actually kind of drew this the wrong way. Let me make this a little more cleaner and better. And I want you to reconsider something. I'm going to redraw this. Now, think about this. First of all, remember what voltage is. Last semester, voltage is a separation of charge. So what I got to do is take some plus charge and take some minus charge. If there's a separation between plus and minus, we call that a potential difference for a voltage. And batteries do that automatically. Through chemical action, they separate charge and create a voltage. But anytime I have a separation of charge, I have a voltage. So imagine I have a piece of copper. And that copper is actually neutral, because I have the same number of plus charges and minus charges in that copper. But I don't know if you remember, we talked about copper in DC. Copper has atomic number 29, which means there's 29 protons. And if it's a neutral copper, I have 29 protons and I have 29 electrons, but look, remember those shells that we talked about in DC? See, this is why I spend time doing that in DC, so I can explain stuff like this in AC. So if you remember that, there was these shells, and the first shell can only hold 2 electrons. The next shell can hold 8 electrons, and then we can keep going. The point is that when I distribute all these electrons, copper ends up with 1 valence electron, and you remember, 1 to 3 valence electrons makes it a conductor, 4 makes it a semiconductor, and 5 to 8 makes it an insulator. Well, this has 1 electron. Now, why is that important? Well, number one, if it's 1 electron, it's a good conductor. And number two, since I have 28 other electrons in here, that 1 electron, that 29th electron, is a long way away from that nucleus. And guess what's holding this electron to the nucleus? The fact that this is negatively charged and this is positively charged. But since this is so far away from the nucleus, it doesn't take much at all to knock that electron off to make a free electron. It takes just a little bit of force to separate this electron from the atom. So imagine this. Imagine I'm just going to show you one. It's silly to show you one atom. I'm going to show you one copper atom. Here's the nucleus of the atom, and there's that 29th electron sitting right there. Weakly held to the nucleus. I can almost do like this and knock it off, just blow it. What do you think happens when I take that copper wire and move it through the magnetic field? Remember, anytime I have electrons moving through a magnetic field, there's a sideways force acting on it. When I move this through here, the force on this electron is going to push it down to one end. If the electrons are pushed down to this end, then what's left, if I have 29 protons and 29 electrons, if I remove this and put them at the other end of the wire, now I charge a plus charge up there. That's the absence of electron leaves behind a plus charge. And so just for a minute, as long as that's moving in there, I have a separation of charge. The minute I get out here, outside of that magnetic field, they're going to go back together, and this will be neutral again. I won't have a separation of charge. But as long as I'm moving in that magnetic field, and the force of this moving, the magnetic force of the electron, the free electron, or the one that can be freed easily, and the interaction between the flux there and the magnetic flux here is pushed to one side. As long as that's happening, I'm going to have a separation of charge. And that only happens when I'm inside the field. So what I'm saying is this, that I can actually take a piece of metal like this and hook up a light bulb to it, and I can move that in and out like this, and depending on the direction, the charge is going to be forced down to one end, so maybe all my electrons are moved down here, and my protons are there. That's a voltage. That's a rate of charge. When I move it back, since the direction changes, this is going to be plus charges, and over here I'm going to have minus charges. Let me talk about this a little bit more. Let me show you another way to think about it. There's something called the right-hand rule. Now, don't confuse this with what we did. We did a right-hand rule when we were trying to find the direction of magnetic flux around the wire. We used the right-hand rule, but this is another right-hand rule. Now, to show you the right-hand rule, I got to show you my little arrow thing again. Remember, if I want to show direction, I can use an arrow. I can show an arrow going like that, or like that, or like that. But how do I show an arrow coming towards you or into the board? If you're looking at an arrow, the tip of an arrow, here's your eyeball, what you see is this. If you're looking at the tail of that arrow, what you see is that. So I can show an arrow, I have an arrow or coming towards you. I can show something coming towards you like this. If I have something going into the plane of the board, I can show you like that. And so there's a right-hand rule which will show you the force on a charged particle moving through a magnetic field. The force of a charged particle moving through a magnetic field. And what you do is you got to take your right hand and your finger. Let me see if I can draw a hand. I can draw a hand. So if I draw a hand like that, this is the right hand rule. If you're writing that down. And what it tells you is the direction of the force on a moving charge through a magnetic field. So your fingers point in the direction of flux. So that's flux. Flux equals fingers. Your thumb points in the direction that the charge is moving. So thumb, this is the direction the charge is moving. The palm of your hand will show you the direction of the force on the charge. So it turns out that the force will be coming out at you like this. So I'm going to draw that as a circle and a dot, so you can see that. Okay, so this gives you the direction of the force on the charged particle. So let me actually do it. So here is my right hand. My flux is going down this way for my permanent magnets. So my fingers point in the direction of the flux going down. My thumb in the direction of the charge. So the charge is moving that way. So let's say I got my charge. I'm putting an electron there, moving that way. Now actually they use a positive charge, but none of that really matters. The point is, my fingers represent the flux. The charge is moving that way, so it's moving into the field like this. When it gets in the magnetic field, the direction of the flux is by the palm of my hand. So, the direction of the force on the charge is given by the palm of my hand. So when I'm moving this way, the force is towards you. If I turn it the other way, now the force is into the board. So if I do my hand like this, I got a circle with a dot. I don't know if you can see that or not. And on the back of my hand, I have a circle with an X. If I'm moving that way, the force, the circle with the dot, is on the palm of my hands. The force is that way. If I'm bringing it back that way, the force is into the board. I'm looking at an X. So I kind of drew this incorrectly last time because I had the force either pulling the charged particle down or pulling it up, and actually move it to the left or to the right using the right hand rule. So going back to that metal pipe. If I have that metal pipe, a copper pipe, and I had those electrons that are easy to knock off the atoms, when I move it through the magnetic flux, these electrons can be pulled down here as long as it's moving through flux, which means that up here I have positive charge. So imagine now that this marker is the pipe. There's the pipe. And I'm going to take this metal and move it in and out like this. If I move it like that, the right hand rule, the arrow is coming out like this. That represents the force pushing those electrons. It's pushing the electrons towards you. The electrons are actually pushed to this end, which means the other end is positive. When I get outside of this flux, that all goes away because I got to have flux to push those electrons to one end. When I move it back, the palm of my hand turns around. So now the electrons are being pushed to the other end. And if I do this back and forth like this, what's happening is from one transverse of the flux of the pipe, I might have this separation. If I bring it back the other way, then that polarity is going to flip because now the force on the charge is the other way. Now, I actually have on Blackboard a really nice diagram of this right-hand rule. I don't know, it's kind of hard for me to explain through the camera, but I really hope you can see this because this is critical to understanding this process of AC. This is why generators can only produce AC. Because when I move it one way, the separation of charge on the conductor is one way. It might be plus, plus, minus, minus. When I bring it back, the force is reversed. So when I'm reading it this way, instead of that way, then if this is plus, plus, or if this is plus, minus, then I have plus, minus like that. And if I move it back and forth like this, if I can see the plus and minus sign on this, when I move it one way, I would see the plus minus one. When I move it the other way, they will reverse. It will alternate back and forth because that force alternates back and forth, obeying that right-hand rule that I'm trying to explain to you. So to make a long story a little shorter, what I'm saying is you can actually make a generator like this. You can take a piece of wire or a copper pipe, and I'm going to hook up a wire to it like that, stand there, and in theory, if I move this back and forth, the light bulb should blink on. When I pull it back, it should blink off. If I do it fast enough, it should blink on and off. When I move it one way, the current is forced to move one way, and when I bring it back the other way, the current moves back the other way. If I stand there and do this, then what happens is the current moves back and forth, and each time it moves, once I get outside of the magnetic flux, the light bulb is going to go out. Faraday says I got to have magnetic flux, movement, and a coil. If I take one of those away, I don't produce a current. So when I go outside of the flux line here, it goes away, and this will turn off. When I pull it back, it'll come back on. So I can do this back and forth, back and forth, back and forth, and the current actually go back and forth, and then the light will turn off and on real fast. If I do it fast enough, it'll look like it constantly stays on. And that's exactly what happens in the lights. If you have AC lighting, they're really flashing off and on, but it does it so quickly, it looks like they're staying on. So this is a generator, me taking the pipe and just doing this. I can actually generate a voltage or current. Now, you might think to yourself, well, that's not a very good generator. If I got to stand there and do this, that doesn't work for me. I mean, I need a better way. How do I get that kind of motion anyway? It's hard to do. Well, that's where Jacob's answer was exactly on point when we talked about turbines or rotating machines. It's really hard to get this kind of mechanical motion out of anything, but it's really easy to get rotational motion. So what they do, instead of having a straight conductor, what's done in the generator is they bend the conductor into a coil. So they take that straight conductor and they bend it into a coil like this. Like that. And you might say, okay, well, why is that such a big deal? Well, here's why. That's a big deal because now what I can do is I can take this and stick it in here like this. Maybe I hook my light bulb up to here. Here's my light bulb. Hook a wire here and a wire there, right? Now I have options. I can put a shaft on this side. So I got a shaft. And connected to that shaft, maybe I got if this is your car, you got a wheel here, a pulley. And you got a belt over it connected to your engine, and that belt will spin that. It'll make it rotate. Or maybe I don't have a pulley. Maybe I have a blade. I got like a fan blade. And I stick that up in the air so the wind can turn it. Or maybe I stick it underwater. Or maybe even better, I make a dam. I dam up a river, and I have water flow over the dam and hit that and spin that. Some kind of way, I make that coil spin in that magnetic field. And when I do that, Faraday says I gotta have a coil. Well, I got a coil. I gotta have a magnetic field. Well, I got the magnetic field. I gotta have motion. Well, now I got motion, but it's circular motion. So I have everything we need to create AC voltage. And that's exactly what we do. It's easy to get rotational motion than it is to get this linear motion. So most machines that create AC are rotating machines. They rotate to produce that motion. Okay, well, all right, I kind of get that. I mean, I kind of don't get it, but I kind of do, you might be thinking. It's all new. I can kind of understand what you're saying a little bit. But I see a problem right off in your machine, Singleton. I see a problem right here. If you look right here, what's going to happen? When you spin the coil in the generator, these wires are going to twist, it's going to break off, and that light bulb is going to go off. So how's your generator going to work? How am I going to get energy out here if the wires are twisted? Well, let's look at that question. Somebody figure that out for us. To get away from the twisting wires, what they did was, they said, okay, what if I imagine a paper towel roll like this. We know on the inside of there you got that cardboard tube. So I got a tube like that. But instead of that tube made out of cardboard, let's say it's made out of copper. A copper tube. Well, I guess a copper tube is called a pipe. So maybe I got a copper pipe, right? But what I'm trying to get at is this. Let's say I got a copper pipe or a copper tube sitting like this. And what I do is I cut this off. I want to make it shorter, so I cut this off. I make it this big. I cut that off, so now I got a little piece of a tube. If I set that up on the side, it looks like this. It's a ring. I cut a pipe and set it up, I got a little ring. So now I take the ring and I cut that in half. So I got a half a circle here and a half a circle here. What they do, instead of connecting the wires directly to the coil, what they do is this end of the coil, they attach this top half of this to it like this. So this end right here, you're looking at, here's your eyeball, you look at that end of the wire, and it would be like right here. And they'll weld that part of that ring to that wire, and then this part of the wire, they'll weld down here. So the wires might actually be, if I try to use my wires are actually sitting like right here. Like that. These wires are showing like that. So now what you can do when you do that, you can take another piece of copper. I can take a piece of copper right here, like that, and a piece of copper right here, like that. And then what I need to do is I gotta get a spring. A spring. And that spring is pushing down that way, and this spring is pushing up that way. It's basically keeping these copper, these are brushes. These are called brushes. That and that are brushes. These springs are keeping those brushes against these half pieces of metal. And so now what you can do is take your light bulb and connect up to those brushes. And this thing can spin around in there 360 degrees and maintain electrical contact. And that's a simple thing I just did, but whoever thought about that was at the time, it was a big thing. These are called slip rings. Slip rings. And people that know motors, electric motors, they understand slip rings. So now this is conceptual. I don't know if they're actually made like this, but this is a conceptual drawing. Conceptually, you can do something like this. They might have wire brushes. It might be done on the way. But this is a conceptual diagram. So now I'm able to rotate this through 360 degrees and maintain a constant electrical contact and light this light bulb up. So we solved that problem of the broken wires. Now, I'm running gas, but I don't want to stop here because I'm almost done with this generator thing. I want to explain one more thing if you're following this. Remember earlier I said, okay, there's actually three kinds of AC. I can have AC that looks like this. I can have AC that looks like this. Or I can have AC that looks like this. Well, the rotating machine only produces one kind of AC, and it's that one. It doesn't produce the triangle wave. It does not produce the square wave. It can only produce the sine wave. And the question is, why? Why is it sinusoidal AC? This is the kind of AC that your house, when you talk about AC, usually you don't mean this or this. You only mean that. Matter of fact, the way it's done is if you say AC by default, people think you're talking about that. If you mean this or that, you got to prefix the word AC with triangular wave or square wave. Triangle AC or square AC. If you just say AC by default, you're talking about that one. So why is it this kind of AC? And so I'm going to attempt to explain that, and then we're going to end this because I've been talking for some hours and I'm tired. So before I do that, does anybody have any questions?
I have a question, but it might be better for the end of class, so you can go ahead.
All right, thank you for that. Let me go ahead and do this. I'll show you this, and this will be a good place for us to start, and I can pick up with the other part of this next time we get together. Right? So what I want to do is, here's what we know. We know that when I have a copper wire moving through a fixed magnetic field, it's going to create forces on electrons, and those electrons that are easy to move will be pushed to one side. And the side that they're pushed to depends on the direction of the wire through the magnetic field. If I move the wire one way, they're pushed to one side. If I bring it the other way, they're pushed to the other side. And whatever side the electrons are pushed to, the opposite side of that pipe has positive charge on it, creating a separation of charge or a voltage. And I can actually use that voltage to power something. The only difference is when I bring the conductor back, the electrons are pushed the other way, and the voltage keeps alternating back and forth. The plus and minus keeps alternating back and forth, which gives us a different direction for current, depending on the direction of the coil to the magnetic field. So it's kind of complicated, but kind of not. But the question is, why is it like this and not that or that coming out of that machine? And so I want to attempt to answer that. So wrap your mind around this. There are four here with a battery. It's chemicals, electrochemicals to separate the charge, create the voltage. With a generator, it's actually magnetic forces separating charge to create voltage. But why does the voltage look like that? To understand that, we have to understand the nature of the force creating the separation of charge. What does that force look like? How does it look? So I want to try to explain that. And then I'm going to end the session. So I'm going to clean this up. A little bit. I'm going to redraw my generator one last time. So here's my generator. Oops, I made that too big. All right, so I got my flux. Now, this is going to be kind of hard for me to show, and this is where that document that I have on Blackboard, the packet, is going to actually show it better. I'm going to do the best job I can, and just try to follow me. And what I'm doing now, guys, most people don't even start with this. They go right to the AC stuff. They just skip over all of this. So what I'm saying is, if you don't understand everything I'm saying, it's okay. But if you do, this is just a bonus because you're really understanding the first principles of how this stuff is created and why it is the way it is. But you can actually get through the course without understanding any of this. But if you can just get a little bit of this, I'll be really happy, okay? So I'm going to do this. Here's my generator coil. Right? There's my coil. And I want to put in there, but I want to do it a certain way. Now let me label this. I'm going to call this side A, and this right here side B. I don't really care about that part. I'm just looking at this wire and this wire. And let's say this is in the position where current is flowing this way. It's flowing in that way and out that way, right? If you were to look at this right there, you will see current coming towards you, which means that you're seeing this. If you look at it in conductor B, you will see current moving away from you, so you will see that, if you follow that. So what I want to do is take this coil I'm going to represent the coil with the markers. And I want to put it over here between the two magnets in the flux so it can rotate. But the problem is I don't want it that way. I want it like that. So I got to show you with these markers. So I'm going to stick this in here like that, and I'm going to spin it that way and put it in the magnetic field. So if I do that, I put this over here. Here's the coil. And I put it over here. I spin it like that. And then if I do that, what you're saying is right here, that's like conductor A. And right here, that's like conductor B. If you can see what I did here. So I took this, I put over here conductor A, I moved it like that, and I spun it this way, and I put it in the field like that. And so now you're looking at this part of conductor A and this part of conductor B. All right, so if you look at that, if current is flowing, well, let's not worry about the current. Remember what Faraday says. Faraday says that if I want to create a voltage, I gotta have a conductor or coil. Well, I got that. I gotta have a magnetic field. I got that. This is the north and that's the south. But the other thing I gotta have is movement. So what's happening is this thing is moving in a circle. But here's the thing. Remember in the video where the guy had one loop and he ran the magnet through one loop and it was a little bit of current produced? He went to 10 loops and he moved it through. It was more current produced. He went to another loop and it was even more current produced. Well, he could have did that a different way. He could have had one loop, like let's say the 10 loop or the 100 loop, and he could have got more voltage and current by adding more magnetic flux. He could have said, all right, I got one magnet. It'll move in and out. It'll create so much voltage that alternates back and forth. But if I have even more flux, it'll create twice as much voltage and current. If I have more magnetic flux, if I make the magnetic flux even more, it'll create more voltage. In other words, adding more, the more flux I cut across, the more voltage I create. That's important, what I just said. The more flux I cut, the more magnetic flux I cut across, the more voltage I create. The more force I create, the more that force pushes charge, separates the charge, which translates to more voltage. Well, think about what's happening here. This thing is rotating. So I got my coil, and it's rotating around, like it's spinning around this way. As this thing is spinning, I'm going to draw this line right here. And that's just my starting position. As this thing is spinning, conductor A is moving up this way and conductor B is moving down that way. They're moving in two different directions. Well, first of all, what that means, remember, if I move one direction, that means the current polarity is going to be one way. If I move it the other direction, the polarity is going to be opposite. If I move back and forth, it alternates. Well, the fact that conductor A is moving up and conductor B is moving down because it's moving like this. It's rotating like that. So one conductor is moving down and one's moving up. That means if the current is coming out of one, it's going into the other. And when conductor A and conductor B changes places, that's going to reverse. It's going to move out of the other and into the other. I don't know if that's confusing or not, but you'll get it. But here's what's important. This represents, let's say, position 1, where conductor A and conductor B are just kind of sitting there, just starting to turn. Just think of that 0 degrees. They're just starting to turn. None of these conductor A and conductor B, they're really not cutting across any flux. You cut across flux, you can't move in the direction of flux. You can't move up and down. Me doing this would not generate a voltage across the wire. I got to cut through it like that, or even like that, or like that. So right at this position, I'm calling it position 1, conductor A is just starting to move up, and conductor B is just starting to move down. You're not really cutting any flux. You got to cut flux. They're cutting any flux at this first position. It's not until it starts to move up like that it starts to cut more and more flux. And at 90 degrees, it's cutting the maximum amount of flux. So right here, the force being created is 0. There is no force created because as it moves up, you're not cutting across any flux. As you get up here, maybe, I don't know, maybe 30 degrees, you're cutting more flux. Then 90 degrees, you're cutting the maximum amount of flux. Then back over here, you're cutting less flux. And when you're back to position 1, you're cutting 0 flux. The force is going to follow that. Right at this position, there's no force. And the more I move towards 90 degrees, the force gets greater and greater and greater until conductor A is moving that way. When conductor A is at this position, moving that way, and conductor B is moving that way, you're cutting the maximum amount of flux. So when I get the maximum force, which is going to give me the maximum voltage. When they change places, the process repeats, but the current direction in each conductor changes. So what does that look like, though? It looks confusing, but what does it look like? Well, I can make it real easy. Let me try to make it a little easier. And then I gotta end this. Which means I'm gonna have a lot of review to do next time we get together. I gotta go back through this, but that's all right. So what I'm going to do is now I'm going to make this really simple because I'm going to take the coil out of the generator and represent it another way, and you'll see it. What I'm going to do is take my generator, here's my coil.
Ron, real quick while you're working, how soon are these recorded versions uploaded to Blackboard?
Within by the next day. Since I'll try to do it the same day for you, Dominic, but I just get so tied up with stuff. It takes a while for to download, but I'll try to get it by the next day for you.
Okay, thank you.
Okay. You can always go though. When you go to Blackboard, your links just say collaborate. You can click on that, and it'll be on. It'll be a while before I put it on YouTube, but it should be on Blackboard automatically once it.
Okay, that's what I mean. Okay, cool.
Yeah, that's controlled by Blackboard, not by me. This is a big file. It can take up to 24 hours to render. Okay, I know guys who've been here a long time. I'm almost ready, but let me show you this, and then we'll pick up with this next class. So here's what we're going to do. We're going to take the coil, put it in here, and I'm going to take an arrow and attach to it like that. So in other words, I'm going to take an arrow and attach to it like that. Now, why am I doing that? Because when I spin this, what's going to happen is that arrow is going to spin around. And the reason I'm doing it is because what I want to do is kind of move away from the generator and be able to show you on the diagram where that coil is. So, if I'm looking at, here's my eyeball, I'm looking at that arrow. If that coil is turned flat like that, then the arrow actually is over here. And as that spins around, what happens, the arrow just moves around in a circle, right? And so what this enables me to do is I can show the position of the coil by the arrow. If the coil is, again, if the coil is flat like this, if it's flat like that, then my arrow is going to look like that. Because my arrow, I can't hold it, but it's off to the side. And as it moves around, this is showing me the position of the arrow. So, how is this going to help us to understand the nature of the force we're dealing with? Well, it turns out that, imagine I have light shining on this. So I got light shining on this. And I have a screen here. And what I want to look at is the shadow of this arrow, which is attached to this. Now, this actually has a name. I know it's kind of weird because I put an arrow over here on this coil, but when I move it to an XY coordinate system, that arrow has a name. It's called a phasor. So now we're getting into some math stuff. This is called a phasor. By definition, a phasor, all it is an arrow whose tail is fixed at the origin of a Cartesian coordinate system. Said another way, it's just an arrow stuck to an XY axis. XY axis is a Cartesian coordinate system. And what that does is it shows the position of the coil in the magnetic field. But it also does something else. If we look at the shadow or the projection of that arrow on a screen, it tells us how the forces are acting as that coil moves around the 360 degrees in a circle in that generator. So what I'm saying is, when this coil is flat like that, and that arrow is off to the side, that phasor is off to the side like that, as it moves around, the conductors are not cutting much flux at 0 degrees. They cut more and more flux as they reach 90, and they go back to a minimum amount of flux until they go back to 0. So at this position right here, if I look at the projection of the shadow on the y-axis, the shadow is going to look like this. So that means that I don't have very much flux, I don't have very much force, so I'm not going to separate very much charge. There's going to be very little no voltage, no current. But as the coil starts to turn, let's say it moves to this position, then the shadow now looks like this. The light will make a shadow like this. And so the length of this arrow actually represents the force created at that position. And you can see what's going to happen, that every time I move, the coil moves and gets closer to 90, the shadow is going to grow. So at 90 degrees, the shadow and the arrow are exactly the same height. They're exactly the same height. So it grows, and at 90 degrees, it's like that, which means the force is greater at 90 degrees because I'm cutting more flux at 90 degrees, which means the voltage and current produced is going to be more. But then as I keep going around the circle from quadrant 1 to quadrant 2, what's happening? I got to move the light source over here, but you can see that as this moves down, the shadow is going to start to shrink again. So the shadow is doing this. It's shrinking until my arrow gets all the way around to 180, and then I'm back to that, which represents no force. There's no force produced at 180 because I'm not cutting any flux when I'm at 0 degrees or 180. But then when I move down here, when my arrow moves to position 3, that coil has moved all the way to position 3. Well, now I have a shadow again, but it's growing in the opposite direction. So what's going to happen is the shadow is going to grow like this. And then at 270 degrees, I'll get the maximum amount of shadow, which represents the maximum amount of force. And then quadrant 4, as I come around, go through one complete revolution, I get the same thing, but now it's back up. It's back up the other way. This will start to shrink until I'm back to a dot again. So I don't know if you actually following this or not. I hope you do. The arrow height is giving us a shape or an expression of how the force is acting. And if I want to look at a graph of that, all you got to do is connect the dots. If you connect these dots, what you get is this. The force is acting like this. And every time it goes around the circle, the force acts like that. No force here. The force rises up to a maximum amount. Then the force starts to drop off back to 0. And then the force flips because of the right-hand rule. It goes the other direction. It starts to push charges the other way up to a maximum amount. And then it shrinks. And then it starts to repeat this over and over again as it goes around the circle. And so if the force looks like this, then the voltage created by the force is going to look like that, and the current created by that voltage is going to look like that, and that is a sine wave. A sine wave. So the AC created by a rotating machine is sinusoidal. Now, as I said before, guys, it's a much better job to look at that handout that I have on Blackboard. So I think what I'm going to do, because this is a little hard to grasp through the camera. It's hard for me to use my props and all of that. So I'm going to make a video where I talk about that packet and the power distribution system that I talked about. It's in there. The generator, it's a picture of that in there I can talk about. And then this sine wave, the creation of how these forces are acting, and produces a sinusoidal voltage is in there with nice pictures. So I'm going to talk about that, and hopefully between my description here and then what I'll give you, that video I'll give you on that packet, you can understand this. Now, if I could keep talking, which I'm not, I'm going to end it now. But now here's where we start to get into the math of this. So I think what I'm going to do is tomorrow I'll make that other video from the packet reviewing this right here. And if you can understand that, then when I get to the math that comes out of this, it'll make it a lot easier to understand. So I think that's enough for today, enough punishment. Anybody have any questions for me before I end the video? Anything we talked about, any concerns or whatever?
I have a question, but again, it doesn't need to be on the recording or anything, so if you want to wait until everybody else is done, that's fine.
Yeah, we can do that. Anybody else have any questions about the material? Anything I talked about regarding what you need, lab, anything? Any questions at all? Okay. Did I have you guys email me or text me or not? I tell you to text me? I couldn't remember. Did I tell you to do that for attendance?
Yeah, I sent mine.
Okay. All right. I couldn't remember. Okay. Anything else? That's it. I'm going to end the recording. If you do have more questions, again, when I do the video, I think it'll be a little bit more clear. I think between this and my video, it'll be clear. And then if you have other questions, you can either wait till Wednesday when we meet again, or you can text me and I'll answer your question. So you guys have a great rest of the day. I'm going to now turn the recorder off. So if